I've had a number of requests to demonstrate the setup for a multi-component M1 or MAB model. And so I thought what we would do is start with our multi-component ideal solution model and extend it. To do that, first step is to make a copy. And I'll name that MAB M1. Oh, let's put it over here next to the put it after the MAB binary. Okay, and then let's take a look at what we're trying to do. In a previous video, I had shown you how to derive this expression for the multi-component situation. And so what we're going for here is this sum of the aij's or akj's for whatever component is component K minus the Gibbs excess energy for the mixture. And here you can see what the Gibbs excess energy is for mixture, just that double sum. And we've got to remember to divide by 2. I always forget that. So let's go ahead and get started. What we're going to need is a matrix then of all these aij type parameters. And I'm going to predict those based on the MAB model. But I'm going to create a space so that you can change those and not wipe out all the things that you've typed in for the prediction. So what I'm doing here is typing in the formula. I'm going to type it in a certain way so that when I make the changes, it's going to copy the cells in a way that makes it easy for me to change. There's no really perfect way to make this work, but I'm going to put F4 to get dollar signs on that, and then I'm going to go ahead and subtract this one, even though I know that's going to be 0, and I want to put a dollar sign there. And then similarly, I want to do the same thing for the betas according to this MAB formula. F4 minus this one with a dollar sign times V1 plus V2 go dollar signs divided by 4. Now I knew that was going to come out to be 0, but now let's make sure. Oh, we better change the compounds. Tell you what, I'm going to push pause here. The compounds we want are isopropanol, water, and MDEA. The basic problem is that we want to break the azeotrope for isopropanol. Between isopropanol and water, and so let's say that's 0.99 and, well, actually let's leave it as 99 and 1. So we're trying to break the azeotrope between isopropanol and water by adding this third component, methyl diethanolamine. I picked that component because the way its alphas and betas align. So you see how the beta is greater than the beta value for water, but the alpha value is less. And so this is going to give us a negative result for the Aij. And so what's going to happen is as we add the MDEA, it's going to moderate the non-ideality of the water, make it more happy and comfortable. And that's going to bring the relative volatility up, or the K value of the water down, however you want to say that, so that the azeotrope no longer exists. We'll see how that works out as we move on with the problem. So we have this number, 3105, between isopropanol and water, and we don't know offhand if that's right, but we have an easy way of checking it. Isopropanol and water, and so let's go see. Yes, the A12 value is 3106, and that's pretty close to what we calculated here. So now we're ready to go on. How many of these we got? That doesn't belong here. So let's copy this over to the next. Actually, let's just copy this one. Less to fix. And take a look at it. And what we see is we should be changing columns here because we want to, like we did here, we want to subtract in each row from the beginning one. But now we want to do that with column number 20, or compound number 20. Now when we copy that down, we see that it should be symmetric, and it is. And I think this is working. So now we want to do the same thing here and just increment this. What did I do? 21, 22, 22, 22. That doesn't seem right. 20, 21. Yeah, how did that happen? 22, 22, 22, 23, 23, 23. Okay, that looks a little more like it. Whoops. Drag that down. We're still getting the symmetry. Everything looks good. Alright. And then over here in the blue zone, we're just going to set those equal. And in the future, if we want to use some experimental data to fine-tune our A12 values, we can just set that up over here. If we mixture changes then and we don't know what the A12 values are, well, we can just set them equal to this again over here. Let's see if we can clean up this thing all at once. There we go. That's a little neater. Okay, now we've got our Aij matrix, and what we need to do is calculate our gammas. First thing that's going to happen is these K values are going to become a function of composition, and so I'm going to need to move them because they're going to depend on the x and the y, because the gamma depends on the x, and K is equal to gamma I pi sat over p. So right now it's just the pi sat over p because that's the ideal solution, but we want this to be for the real thing. Yeah, okay. Alright, I think we're set now. We're ready to go. We just gotta go and get those gammas. So I'm going to need a little space here. Just going to move this over 2 spaces. So let's calculate the RT-AIMK matrix. Let's call it that. Or vector, really. Because what this is, I need to multiply my x's times my aij's here in order to get that formula that we were talking about. This thing, right? So I need to get the sum of the x's times this akj column. And then what you're going to see is just summing that up will give us the delta GE quantity. So I need to take the sum product of the x's, and I don't want those to change, with the aij's Now here's a tricky thing, because those numbers change in a slightly unpredictable way, where the just simple copy function doesn't work. But what I can do is grab that column there and move it over. It's kind of a cute trick. The original Excel couldn't do that. That was back in 1995. All right. Now we got the sum of our x's times, make sure of that. Yep, x's times our aij's. And if you think about that carefully, what you'll figure out is the Gibbs excess, the double sum, is just equal to the sum product of these x's with those AMKs. I call them AMKs because they're sort of component K interacting with the whole mixture. Oops. So that would be GE times 2, and I forgot to divide by 2, as I always do. Now we're ready to calculate our gammas. And it's equal to this minus that. I don't want that to change. Oh, wait a minute. It's equal to the exponential of that. Parentheses everywhere. Divided by 8.314 divided by t, and I don't want that to change. It looks more like it. Okay, it should be around 1 because it's practically pure isopropanol. And we see that it's negative between the MDA and the water, and kind of expected that. I think that looks all right. And now we have to modify our k-value expression here to be gamma times that. Alrighty. Now finally we want to calculate our relative volatility of the light to the heavy, but that's easy. That's just the k-value divided by the k-value. And we wanted to do this at 363. So, okay. I think we're ready to add some MDEA now. And so let's try 10 of that. Well, let's just first show you that the problem here is that the relative volatility is 0.62, at the high end of the IPA range, but at the low end of the IPA range, we see that it's 4.6. So it's changing from something greater than 1 to something less than 1. And that's how we know we've got an azeotrope. So let's add some MDEA and see if we can help that situation. Let's try 10 of that. The less we add, the better off we are. We have an easier separation downstream. We moved in the right direction, but not quite enough. Let's try 20. Getting there. Let's try 30. Okay, went too far. Let's try 25. Pretty close. 27. Real close. 26.5. Okay. And we've gotten to a point where the azeotrope is broken. We've got a relative volatility of 1.2. That's a reasonable distance from 1.0. And I want to show you one more thing here. Sometimes when we're doing a dew point calculation, these calculations get to be broken, essentially, because the mole fraction of the liquid affects the gamma, and the gamma affects the K, which according to this formula affects the gamma, which affects the K, which affects the X, and so on. The reason we got out of that here is because we set our mole fraction of vapor to be equal to practically 0. So let's see what happens if I just instantly type in 999. You see it breaks it. You can't just jump all the way to the dew point. And so that means we've got to go fix our K values. I'll just make that 1 again. Alright, so now we're back to the ideal solution approximation. Let's make that 001 again. Everything's fine, everything's working. Change our K values back to the gammas. Alright, we've recovered. So that took about 30 seconds. So whenever you see this thing crash, you'll know how to fix it. And now what we can do is sneak up on that dew point calculation. And really, we ought to be calling the solver to update our temperature until the D sum to 0 and so forth and so on. And what we see is the dew point goes up as we have the temperature goes up as we approach the dew point temperature. So let's go to 0.8. I'm getting more cautious now. 0.9. 0.95. 0.99. Let's go all the way. Ta-da! We solved the dew point. Look how much higher it is. Wow. Okay, so that way you can recover from any kind of mistake you might run into. That's all I got to say.